Well, it'll make understanding lecture right now make more sense, right? I mean, you know, so let's see here. So just to get us started here, remind you, these are basic rules of differentiation we already know, right? We pull out a constant, we can break up across sums. The derivative of a constant is 0, right? I'm assuming C is a constant here. This is the power rule. Derivative of x to the n is nx to the n minus 1. Specific instances of that, it's good to have memorized, would be, for example, derivative of the square root. It's 1 over twice the square root function. Derivative of the reciprocal functions, minus 1 over the square of x. Derivative of e to the x is e to the x. Derivative of cosine is minus sine. Derivative of sine is cosine. All of these results we had to derive from a limiting process, right? And then also, we have further rules of differentiation, right? Well, yeah, we'll get there, but the derivative of the product, right? We have the product rule. We have the quotient rule, right? I'll write that one in prime notation. Well, I'll write it kind of partially in prime notation. d dx of the quotient is f prime g minus f g prime divided by g squared, right? And then we had the chain rule. I'll write in terms of g of u. d dx of g of u is dg du times du dx. And oftentimes, as you're looking at my homework solutions, at least at the start, I'm expressing this more in the following format, like derivative with respect to u of some expression g of u times du dx. That's how I'm actually implementing the chain rule, sort of just as in terms of symbol pushing. I think the thing to remember is, okay, I know this function, I know how to differentiate it, right? But if I'm differentiating with respect to a variable which is not the variable that's appearing inside the argument of the function, then I need the chain rule, right? So if I'm differentiating with respect to x, but I'm looking at g of u, then I have to multiply by the derivative of u du dx, and I have to take the derivative of g and evaluate at u, right? This is the chain rule. Now, what else was there? The what? Prime of a prime? Well, that's true. We did talk about f prime prime of x. That notation means like second derivative, right? You what? Yeah, I asked a couple of higher derivatives on the homework. Another thing that we've talked about briefly, but we should come back to from time to time, is the application of time, right? We could have position. We could say x of t is the position at time t, right? Position at time t. We could have the velocity, and to be more precise, the instantaneous velocity, v of t, at time t, that would be dx dt. And we can have acceleration, that would be a of t, which would be dv dt, which would also be denoted d squared x dt squared. I don't know if I've used that notation in here yet, but the second derivative, another notation for this is d squared f dx squared. That means second derivative with respect to x of f. Okay? So that's an important application, position, velocity, acceleration. Of course, that's what motivated, in part, Newton to discover calculus and put it into practice, right? But we're more focused on questions of geometry in this class, right? But we do entertain physics from time to time. Now, you told me about 5 minutes ago, I don't know, 2 minutes ago, we know other derivatives. What else have we worked out like last class? Let's see here, I'll put down here, we also know that d dx of cosh x, yeah, Cinch and cosh. I said cosine last class where I meant to say hyperbolic cosine. I was watching the video back later. Sorry about that. So this is interesting. Hyperbolic sine and hyperbolic cosine, they're each other's derivatives, but there's no minuses. Like the sine and cosine, there's a minus with the cosine, but there's a plus with the sine differentiating. Hyperbolic sine and cosine in contrast, just like that. Now what else do we do? Remember we did tangent? What was the derivative of tangent? Yeah, secant squared theta. And what did we find the derivative of secant theta was? So both tangent and secant we could derive from the quotient rule, right? Because secant's 1 over cosine, tangent sine over cosine, so we could use quotient rule. And derivative of secant was secant tangent. Now, do you guys remember what was the derivative of cotangent? And what was the derivative of cosecant? So derivative of cotangent actually ends up being minus cosecant squared. And derivative of cosecant is minus cosecant cotangent, as it happens. Are there any other basic functions that we know about that we have not tried to differentiate yet? How about, let's work out, I know one we haven't done yet, derivative of hyperbolic tangent. Oh, what's that one? What is the hyperbolic tangent? It's a hyperbolic secant. Well, that would be a good guess, but let's see if that's right. Cinch x over cos x, right? That's the definition. And so this is a quotient rule, right? So we use quotient rule. I mean, it's a quotient, so we use the quotient rule. And so the derivative of, let's see here. I'm going to show you. This is a notation I haven't used in here yet, but students like this notation. I'm kind of, it tends to get students into trouble, so I probably shouldn't show it to you, but it is an efficient and easy notation. It saves you guys writing if you use it, but you got to use it correctly. So derivative of sinh is what? Cos, right? So we've got cos squared x minus sinh squared x. What is cos squared minus sinh squared? Well, one of the fundamental identities for cos and sinh is that cos squared minus sinh squared is in fact 1. So it turns out you were right. This is 1 over the hyperbolic cosine of x quantity squared, right? So we could write it like this. And what we would have is indeed hyperbolic secant squared of x, all right? So indeed, we could add to this list ddx of hyperbolic tangent is equal to hyperbolic secant squared of x. It does work out that way. Now, I'm not going to do them all in here, but you can go through, and it's a good exercise to try to differentiate the other hyperbolic functions like hyperbolic cosecant x and so forth. All right. So just want that all out in front of us, all right? And now I'm going to talk to you about sort of the next part of our thinking in differentiation, which is what's called implicit differentiation, all right? So the idea of implicit differentiation, so what's this word mean, implicit? Implicate? Yeah. Implication? Implicit. What's explicit? dangerous. Here, let me show you the difference. So if we write x squared plus y squared equals to 1, right? This means that that makes y an implicit function of x. Right? In contrast, if I say, y equals to, say, 3x minus 7, then you can say, aha, this is f of x, right? So this says y is explicit function of x. So explicit is when you can just plainly solve for whatever it is you're talking about. Implicit is when it's sort of tied up in something that you may or may not be able to unravel, right? Like this one, x squared plus y squared equals to 1. Could we solve for y? I mean, we could, right? You solve this for y? I mean, y squared is what? 1 minus x squared, right? So we get, excuse me, we get y is equal to plus or minus the square root of 1 minus x squared, right? So is y a function of x? Let me draw a picture. Right? If you look at this, the answer is, well, maybe. I mean, definitely you can get the top half of the circle from the plus, right? And you can get the bottom half of the circle from the minus, right? But can you get the whole circle? Can you get the whole circle as a graph of a function? I mean, we talked about this a while ago, but the answer is no, right? Because you failed the vertical line test, right? So can we write, so this is the question, can we write, let me start us out right. Given x squared plus y squared equals to 1, can we write y equals to f of x, for some choice of f? The answer is, it depends, right? It depends on where you are, right? So the answer is kind of a little bit complicated. Well, if y is greater than 0, then we choose f of x equal to the square root of x squared, 1 minus x squared, right? On the other hand, if y is less than 0, then what? We can solve for f of x is equal to minus the square root of 1 minus x squared, right? What about if y equals to 0? Can we solve for y as a function of x near y equals to 0? See, if y equals to 0, if you were to try to write the points in the circle as a function of x for points near 0 for y, you'd be out of luck, right? Because you'd either be looking at this or you'd be looking at that, right? And in both cases, when you're at y equals to 0, if you're close to that point, what happens? Right? If you're going to try to include where y is equal to 0, it forces you to violate the vertical line test, right? So it's not a function. All right? So it's not automatic that when we're given an equation in terms of x and y, we can necessarily solve for y as a function of x at a given point, right? It's a local thing. If we're given a point, and it's the right kind of point, we can solve for y as a function of x. But that's not guaranteed, all right? And actually, answering when it's guaranteed is beyond this course. This is a problem that's addressed by advanced calculus in something called the implicit function theorem. The implicit function theorem tells you when it is or isn't. Well, it tells you when it gives you criteria for your equation, which will guarantee that you can solve for y as a function of x, right? But since that's beyond our pay grade, what we're going to do in here is we're going to take a rather cavalier approach and say we're going to assume, given an equation, that we're at a point where we can solve for y as a function of x, and we're just going to go on that basis. All right, so that's our MO in here. Our MO is going to be assume, that there exists a function which makes y a function of x near the point of interest. I mean, we understand that this is a local idea, right? We've seen from the circle example, we can't find y as a function of x for the whole solution set to the equation. Thought maybe one of your, oh well. But at least we can do it locally, all right? So what I was just telling you isn't really calculus, right? Like everything I've been talking about for about the past 3 or 4 minutes, this is just algebra. But, all right, so here's the deal. We're assume that there exists a function which makes y a function of x near the point, and that dy dx exists. All right? So that's the idea of implicit differentiation. We're going to assume that you can solve for y as a function of x. And we're going to go forward on that point. So, for example, well, let's start out with something simple where we actually can solve for y as a function of x locally. We even know how. This one, right? X squared plus y squared equals to 1. Let's calculate dy dx using implicit differentiation. So, implicit differentiation, what you do is you just straight differentiate the equation with respect to x, right? So we have d dx of x squared plus y squared equals to d dx of 1. So what's the difference between this and what we have been doing? What we've been doing up till now is we've been differentiating a given function, right? That's explicit differentiation because you're given the function and we differentiate, right? Now I'm differentiating an equation. And notice, so the first piece of this just gives me 2x, right? But then what do I have? I have d dx of y squared. And what is that? The other side's 0, right? Derivative of 1 is 0. So what do I have to use when I'm differentiating y squared with respect to x? Remember I was talking about at the start of class, when we differentiate an expression where the letter is different inside the expression than the differentiation variable, we have to use the chain rule, right? So this gives me 2x plus 2y times dy dx by the chain rule. And that's the best I can do. That's the best I can do because I don't actually know what y is, imagine for a second that we hadn't done the algebra on the previous board for a second, okay? Then you could still do this, and what you would find is that dy dx is equal to minus 2x over minus 2y, right? So dy dx equals to what? Minus x over y. So when we do implicit differentiation, typically the answer is not just going to be in terms of the independent variable x, but it'll also involve the dependent variable y, right? Here, x is independent variable, y is the dependent variable in my thinking. Now, that's just a choice, really. X and y appear symmetrically in this problem. You could just as well say dx dy is equal to minus y over x. You could do that. Now, if I'd asked you to find dy dx at a point in the circle, what would you have done before I showed you this example? What would you probably have done? I think what most students would do, just skip it. You say, no. What most students would do would be, but without implicit technique, okay? So we go, okay, well, y is equal to plus or minus the square root of 1 minus x squared, right? And then we differentiate. And we get dy dx is equal to plus or minus 1 over twice the square root of 1 minus x squared times the derivative of the inside function, which is 1 minus x squared. And that gives me minus or plus 2x over 2 times the square root of 1 minus x squared, which gives me minus x over plus or minus the square root of 1 minus x squared. So hooray, there's a formula. But of course, this is minus x over y. So we don't disagree. We don't disagree. It's just that the implicit technique gives me the formula in terms of x and y, whereas the explicit would give me, the other. When I multiply a plus minus by a minus, it gives me minus plus. It's just a notational trick. So the second thing I just showed you, you might be like, well, I don't need implicit differentiation, right? Because I can just solve for y. Why do I need implicit differentiation? What if you can't solve for y, right? Here's one. How about this? X, y cubed plus e to the x y squared equals to tangent x. Find dy dx. All right. Can you solve that for y? I mean, I can't. All right. There are plenty of expressions that we can't solve for y. All right. Like, this is the thing. The implicit function theorem gives us the existence of this function, but it doesn't actually tell us how to specifically find the formula for it. It just tells us that it exists. It's out there. It might only exist as sort of like a numerical method or something, all right? There doesn't have to be a nice formula for it. But we can still do implicit differentiation and understand how the derivative of y and x relate. So we differentiate this. And what am I going to have to do? Differentiate with respect to x. So I got a ddx of xy cubed, right? Plus a ddx, a derivative of e to the x times y squared. And all of that's equal to ddx of tangent x, right? So what are we going to do? So we just take it one piece at a time, right? So product rule, I've got dx y cubed plus x times ddx of y cubed by the product rule, right? Those two terms come from this one. And then plus, well, e to the x times y squared plus d dx of, plus e to the x times d dx of y squared. All of that is equal to, well, secant squared of x, because the derivative of tangent was secant squared, right? So I did the product rule a second time, right there. Those two terms. Derivative of e to the x is e to the x, so I just did it. Now, chain rule. So I've got y cubed plus 3x y squared times dy dx plus e to the x y squared plus 2y e to the x times dy dx equals to secant squared x. Now, I wrote those terms in the order which I find them to be aesthetically pleasing. It might not directly square with your calculational next step. All right, let's think through it. Derivative of the y cubed, right? What was that? Derivative of y cubed is 3y squared, right? My bad. Sorry to the people who aren't here. I neglected to pan back over there. My bad. So, all right. So we differentiated this with respect to x. We have product rule for that, product rule for this. We added the derivatives because it's a sum. Derivative of tangents over here. Derivative of tangent, secant squared. This term gives me the product rule. The product rule gives me these two terms. Product rule gives me those two terms by that one. But this is differentiating with respect to x, y cubed. So I have to do the chain rule. And here it's the cube function. So I get 3y squared times the derivative of the inside function here, which was y. So the x just rides along, right? So this x is that x. Next, I have e to the xy squared, which is still what it was. And then over here, what's the derivative of y squared? Well, I have 2y, right? And then dy dx from the chain rule. And e to the x still, this one is that one. All right, so now that we're here, can you guys tell me how to find dy dx? Because if you understand this example, you can do pretty much any of the plain Jane implicit differentiation problems. Like the algorithm is the same for all of these. You differentiate the equation with respect to x. You apply the chain rule wherever you have a y, do usual rules of differentiation, and then you solve for dy dx. And that's how to find dy dx. This extra step of solving for dy dx was never present before because we always had y equals to stuff and we differentiated it, right? So that was dy dx equal to the derivative of the stuff. Like this extra step of solving for dy dx never happened to us before because we were looking at explicit problems. But check it out. So I've got this term, right? And I've got that term. So I'm going to keep those on the left-hand side and factor out the dy dx. I've got 3xy squared plus 2y e to the x times dy dx, right? Equal to what? Equal to secant squared x, right? Minus what? Minus y cubed minus e to the xy squared. And then I divide by whatever the coefficient of dy dx is. And there's the answer. So dy dx is equal to secant squared x minus y cubed minus e to the xy squared, all divided by 3x y squared plus 2y e to the x. There you go. That's the answer. This is called implicit differentiation. Can you guys tell me a point on the curve? Let's add on to this example. Let's find the equation of a tangent line to this curve. So can you guys tell me one point on this curve that we could make an example for? Can you tell me one point on the curve? How about you, Taylor? Any ideas? No. No? Do you want to try? How about, what if we put say x equal to 0, that may be too greedy. X equal to 0, that's going to force me to put y equal to 0, that's no good. Put x equal to 1, okay. Ooh, I want to get rid of the y. Let's put y equal to 1. Oh, still nasty. Oh. Oh, this is very unpleasant. I don't want to work this one. This is fine as like this. Like, I don't want to find a point on this curve. I just realized it's just bad. It's very bad. Okay, so it's fine. We can move on here. So there is a technique of differentiation, all right, that is based on this idea called logarithmic differentiation. And I think I'm going to do that. I think I'll probably cover that Wednesday, unless we find time at the end of class today. But I can either do logarithmic differentiation now, or I could do it after. But I think logarithmic differentiation is kind of better after the next thing I'm doing. So I'm still kind of recovering from the compression of the schedule that happened from Monday's weather last week, you know. Okay, so this week, just to give you sort of a snapshot ahead, we're covering how to calculate the derivatives of inverse functions, the technique of logarithmic differentiation, and then also what are called related rates problems, right? So I can already show you a related rates problem if you're interested, just to kind of get ahead a bit. That circle problem, it all really falls under the same umbrella of thinking. If Bob travels circle, let's say x squared plus y squared equals to 1, then differentiate with respect to t, right? So what do I mean by that? Well, I mean if Bob is traveling, right, we can think about the coordinates of Bob, x of t, y of t. Well, x and y are both functions of time for Bob, right? I would point out they're implicit functions of time. See, I don't have enough information. I only have a partial picture of this situation. I don't know how fast Bob is going around the circle. I don't know if he's like going at a non-constant speed or if he's like going faster and faster and faster. I don't know those details. All I know is that he goes around the circle, right? And that's enough to relate how the x and the y velocities relate. See, because we can differentiate that with respect to time. And differentiate the other side with respect to time, right? And derivative of 1 is 0. And over here, I have to use the chain rule. So what I get is I get 2x dx dt plus 2y dy dt equal to 0. And that's pretty much it. That's just about all we can say. That's how the x and the y velocities have to relate if Bob's going in a circle. You can't just choose both of them willy-nilly without regard to each other. They have to match this pattern if Bob's going in a circle. In other words, the rate of change for x and the rate of change for y are related. This is an example of a related rates problem. We'll come back to this at the end of the week, work all kinds of applied problems, okay? But see, at this point, I'm going to turn back to functions and just point out there's some things suspiciously missing from our list, right? Like, what have we not learned how to differentiate yet? How about natural log? Do we know the derivative of natural log? What about the inverse sine and inverse cosine, right? What about 2 to the x? See, that was an oversight in your homework. I shouldn't have asked you to differentiate 2 to the x in that one problem. I won't take off points if you didn't get that one, because that was technically supposed to have been covered before in the homework, right? You guys might have just looked it up and done it anyway, right? What was the derivative of 2 to the x? Maybe you looked it up. d dx of 2 to the x, we're going to see why shortly. It is the natural log of 2 times 2 to the x. Right. Now, I can actually show you why that is now. So let's see here, example. This is actually, sorry about this. This is actually a little bit of a digression from the inverse function discussion. But if we want to differentiate a to the x, one way we can learn the derivative of a to the x is by simply doing this. That's d dx of e to the... Oh, I'm now remembering what the trouble is. I was going to do this. Well, hold on a second here. Maybe we're okay. That's an identity because a to the x is positive, so we can rewrite a positive thing as e to the natural log of that positive thing. And then by properties of logarithms, we can pull out the x, right? We're okay. And then what? What do we do? Right, I mean, we let u equal to x times the natural log of a, right? Here a is a constant, so we just do that. So I have d du of e to the u times du dx, right? Which I'll write as d dx of x log a, which is what? This just gives me log a, and that gives me e to the u, which is e to the x log a, but then undoing the algebra that I just did, that's log a times a to the x. So the derivative of a to the power x is the natural log of a times a to the x. Now, the derivation I just showed you is admittedly a little sneaky, because I'm using this, one of my favorite tricks, to rewrite something positive as the exponential of the natural log of that thing, right? And because I already know the calculus of the exponential function, it allows me to figure out the derivative of the exponentials of other bases other than the base e. Okay. So, great. Let's talk about inverse functions. And so we're going to find another way to derive the previous example once we know a little bit more about natural log and how to differentiate it. We'll find another way to do that at previous example, which is a little bit less sneaky, okay? But our first example would be this for the inverse function derivatives. So I'll call this 1. What if we have y equals to the natural log of x? All right. I would like to calculate the derivative of this. But what's the trouble? I don't know how to differentiate the log, right? That's the question. How can we get rid of log and change it to an exponential? How about this? Exponentiate the equation, right? This says that e to the y is equal to e to the log x. What's e to the log x? It's x again, right? Now I have e to the y is equal to x. So differentiate implicitly with respect to x, right? So I have d dx of e to the y is equal to dx dx. What's dx dx? Well, that we know. That's 1, right? But what's what's d dx of e to the y? Well, that's by the chain rule, e to the y times dy dx, right? Now, let's solve for dy dx, because that's what we're after, right? One over e to the y. But what was e to the y equal to? It's up here. X, right? So we have dy dx is equal to 1 over x. So we have derived the rule for the derivative of the natural log, namely that the derivative of the natural log of x is equal to 1 over x. Now, this is for x positive, all right? So, hooray, there you go. Now we can return to the previous example now that we have this newfound knowledge and work it out a different way, right? So previous example, take 2. So we have y equals to a to the power x, right? We're trying to differentiate that. So what we could do is we could take the natural log of the equation, right? Take the natural log of this equation, what do you get? Natural log of y is equal to the natural log of a to the x. What's natural log of a to the x? Well, that's x log a, right? By properties of log. Now I can differentiate that equation with respect to x. What happens? See, we couldn't do this before. Why? We didn't know how to differentiate the log before our last example. But now we do, so we can. But if I'm differentiating with respect to x, what do I have to do here? Natural log of y, right? That we're differentiating with respect to x, but we have natural log of y. So I have to do the chain rule, right? So I have 1 over y times dy dx is equal to the natural log of a, because derivative of x with log a is just log a, because x differentiates at 1, and log a is just a constant, right? And so there you go. Solve for dy dx. What we got? Natural log of a times y. In other words, d dx of a to the power x is natural log of a times a to the power x. So my take 2 does not involve using that super sneaky identity, right? It's just implicit differentiation properties of logs. Which do you think is better? Probably the second one. But the first one would have been a good thing to show you last week before your homework mission 5 was due, right? Because I asked you to differentiate 2 to the x, and I don't mean for you to have to like search out, like the derivatives that appear in the homework should have been ones we've already talked about. So if you see something like that, do email me if you want. If you don't, it's fine. But if you're like Did I miss something? You know, maybe you didn't. Maybe you just overlooked something. Okay, so hey, there's another one to add to our list. Right? d dx of natural log of x is equal to 1 over x. What other inverse functions do we want to take the derivative of? What's that? I do what? I didn't quite follow your question yet. So for the example number 1 and the take 2, in both of these cases, I called whatever I was interested in finding the derivative of y. Then I took an operation. I did something to the equation to change it to something I knew how to differentiate. For example, number 1, I took the exponential of the equation. For number 2, I took the natural log of the equation. But I didn't just differentiate the original equation. I changed it a little bit so that it was something I knew how to differentiate. And we could solve for, I mean, you could solve for y, sure, but then that kind of destroys the whole, what's the word? The flow of the argument, because on all these examples I'm about to show you, we do not, at the moment, know the derivative of the function. So like I can't just calculate dy dx directly. I'm going through some kind of sneaky around the bend argument to get it. Here's another one. 2. Let's calculate the derivative with respect to x of inverse sine of x. Now, before I get into this, it would be good for us to just take a moment to learn a little theorem about a function, the relation of the derivative of a function and its inverse, right? So how are the rates of, how is df dx and df inverse, the derivative of the function and the derivative of the inverse function, how are they related? So let me just kind of go over here. Side note, theorem. Well, it's not really a theorem. It's more of an observation. So if we have f of f inverse, I'll say f inverse of f of x, all right? That's equal to x again, right? By definition, inverse function. What happens if you differentiate this? Differentiate this. We get df inverse dx at f of x times df dx equal to what? Well, dx dx, right? Which is 1. So what this says, it says that the product of, f inverse prime at f of x and f prime of x must be positive. I mean, it says more than that. It says it's 1, right? But because it's positive, think about that. What does that mean? If the derivative of the function is positive, what can you say about the derivative of the inverse function? Also positive, right? What if the derivative of the function was negative? Well, then the derivative of the inverse function must also be negative. Otherwise, we wouldn't get the product of them was positive, right? Either has to go plus plus or minus minus. That's helpful to us as we're working out example 2. It's just an observation. Okay, so look, the way we're going to do number 2 is exactly the way we did number 1. There's an algorithm that we follow here. Like step number 1 is to write y equals to the thing we're interested in finding the derivative of. So in this one, y equals 2 inverse sine of x. Then what's my next move? My next move in number 1 was what? It was to solve for x, right? So our next move in number 2 is going to be to solve for, how do I solve for x in number 2 here? How about I take the sine of the equation, right? So sine of y is sine of inverse sine of x, which is what? Just x again, right? Now, what was my next move in example 1? I differentiated implicitly with respect to x. So we're going to do the same. Differentiate implicitly. So that gives me d dx of sine y equals to dx dx, but okay, so left-hand side, I have to do chain rule because I'm differentiating function of y with respect to x, chain rule again. So this gives me cosine of y, dy dx, equals to 1. So I get dy dx 1 over cosine y. Now that's not a very good answer. We want answers in terms of x, right? We would like an explicit formula for the derivative of inverse sine. So what do we know about, how are sine and cosine related? Remember? We know cosine squared y plus sine squared y is what? One, right? So that tells me that, this is very annoying actually, cosine of y is equal to plus or minus the square root of 1 minus sine squared y, right? But my question is, are we going to choose the plus or the minus in y? So sine is the inverse function here, right? And the derivative of sine is cosine. So whatever, if cosine is positive, we got to choose the inverse function derivative to be positive. If cosine is negative, then we have to choose the inverse function derivative to be negative, right? But if you think about that, that means we just need to make it match cosine. So we should choose plus, I think. Oh, goodness gracious. How to say this? Oh, I'm an idiot. No. Wrong argument altogether. We have to think about what inverse sine means, right? What does that mean? If you plug in an inverse sine, try plugging in your calculator between -1 and 1, what do you get out? If you try plugging it in, you're going to get numbers between plus or minus pi over 2. All right? Plus or minus pi over 2. That's because inverse sine, it's actually the inverse of sine restricted to this piece right here. Right. I don't know what I was just saying. The other thing I was just saying, just total nonsense. But anyway, so that's inverse. That's the part of sine which is inverted. So if we look at sine from minus pi over 2 pi over 2, is it you have a positive or negative derivative? Well, it has clearly a positive derivative, right? So since it has a positive derivative, since y equals sine x has a positive derivative, we must choose the plus for the derivative of the inverse sine, because the part of sine which we invert is increasing, right? You could imagine an alternate universe where you defined inverse sine to give values between like pi over 2 and 3 pi over 2, and then the derivative of inverse sine would be negative. But we didn't do that. In pre-calculus, we defined inverse sine to be with respect to this part of sine. It's a local inverse. So anyway, this is dy dx is equal to 1 over the square root of 1 minus sine squared y. But what was sine squared? What was sine of y? Remember, up here? Sine of y is x, right? So this is 1 minus x squared. You could have put the sine of y equal to x earlier, but there it is. I'll write it over here. d dx of inverse sine of x equal to 1 over the square root of 1 minus x squared. I think you can see why I would recommend this is something that you memorize going forward, right? You could, I mean, you should also be able to derive it. Like, I expect you guys to know these steps, be able to recreate them in your own fashion, all right? There's homework problems like this. But, I mean, clearly this is something we'd like to just know as a point of reference, you know, because it's like a pain to work it out. So in your homework, problem 88, I have calculate the derivative of inverse cotangent. All right. And let's see what else. Inverse cotangent. I also have inverse hyperbolic cosine is problem 94. So I guess I've just asked you 2 of them, but it would be good for you to practice the ones we do in class as well. Let's do inverse tangent so that you have a better sense of how inverse cotangent is going to go. All right? All right, let's get to it. 3. What is the derivative with respect to x of inverse tangent of x? Well, it is, I think the derivative of inverse cotangent is somewhat similar. That's true, but I would work it out. I actually don't remember the derivative of inverse cotangent right off the top of my head. This one, though, I do. This one's pretty famous. This is something you're expected to know going forward. Like if I was a Calculus 2 instructor and I found out that the derivative of inverse tangent had not been covered in Calculus 1, I would be very annoyed. All right, like this is standard, straight down the middle, you know. Okay, so y equals inverse tangent of x. Step 1, call y what we want to find. Step 2, solve for x. Tangent of y equal to x. Step number 3, differentiate implicitly with respect to x. So d dx of the tangent of y is equal to dx dx. Derivative of tangent, we worked out last time. It was secant squared. Or the time before, I forget at this point. Secant squared y, but I have to multiply by dy dx because chain rule. Now I solve for dy dx. I get 1 over secant squared y. I resist the temptation to rewrite that as cosine squared y because it's not helpful. But I embrace the temptation to remember, you know, things I know about tangent and secant, right? For example, if cosine squared y plus sine squared y is equal to 1, then dividing this by cosine squared gives me 1 plus tangent squared y equal to secant squared y, right? Which in our current jibber jabber is 1 plus x squared equals to secant squared y. Because remember, tangent of y is x, right? So, hooray, this shows me that d dx